Hello everyone, today we're going to consider the Sommerfield approximation in statistical physics. So the Sommerfield approximation is a low temperature approximation of the Fermi-Dirac functions, and this is quite useful when considering the Fermi-Dirac distributions in the low temperature limit. So the first step is, of course, to remember what the Fermi-Dirac functions are. So they're shown right here. They are labeled by an integer n. Sorry, not an integer, just a real number in general. And it has this integral representation. And the first step is to split this integral into two parts. So this is going to be, I'm going to grab the gamma function out. So I'm going to get two integrals. One runs from 0 to beta mu, and it's an integral of x to the power of n minus 1, and I'm going to write this as 1 minus 1 over 1 plus ze to the minus x. Okay, and this is very easy to check that it gives the same result as this, because you get a ze to the minus x in the numerator, and that cancels out in the denominator. Dx plus another integral from b mu to infinity of x to the power of n minus 1 over z inverse e to the x plus 1. Okay, so I've just rewritten this as usual. Okay, this can be calculated more or less. So, this can be calculated. So this is equal to b mu to the power of n over n. And then we have minus integral from 0 to beta mu of x to the n minus 1, 1 plus z e to the minus x dx, plus beta mu to infinity x to the n minus 1 z inverse e to the x plus 1. Okay, now we have two different exponentials. So we have z e to the minus x, right? So z e to the minus x, but that's actually e to the beta mu minus x. And then we have z inverse e to the x, but that's just x e to the x minus beta mu. So because we have these two different exponentials, this suggests that we use the substitution of a change of variables. So eta 1 is equal to minus x plus beta mu. So this is the first exponential. Yes, it's the first exponential. And then the second one, the second eta 2, is just the second exponential. So x minus beta mu. Okay, and if we do this, well, what do we find? We get that gamma n f of n z is equal to beta mu remains the same. Okay, now this first integral, we use the first variable, eta 1, so that this minus becomes, what we'll do with that later. So first of all, this is an integral from 0, so let's look at it like this. So what does 0 become? 0 becomes plus beta mu. Okay, what does beta mu become? That becomes 0. Okay, and then becomes x to the n minus 1, but that is equal to beta mu minus eta 1 to the power of n minus 1 over 1 plus e to the eta 1. Now dx becomes minus d eta 1, so this becomes a plus, but I don't like these integral bounds, so I'm going to switch them and get a minus sign here. So this goes back to being a minus, only that now I get e from 0 to beta mu. Okay? And similarly here, what we find, we get plus integral. So beta mu goes to 0, right? Infinity remains infinity. And this becomes b mu plus eta 2 to the power of n minus 1 over e to the, 1 plus e to the eta 2 d eta 2, right? This is much simpler to do. Now, let's look particularly at this integral from 0 to beta mu, right? So if we look at that, note, integral from 0 to beta mu of beta mu minus eta 1 to the power of n minus 1 over 1 plus e to the eta 1 d eta 1. I can write this as an integral from 0 to infinity of, let's call this stuff minus minus the integral from beta mu to infinity of stuff. Okay? But the total integral from 0 to infinity of this stuff can be checked to be very small, of order z to the minus 1. So this is of order z to the minus 1, so very small. So to within a very good approximation, to a fairly good approximation, what I can do is I can take the left-hand side to be equal to just this second integral on the right-hand side, gamma n times the Fermi-Dirac function is equal to, again, beta mu to the power of n over n plus integral, and I write all of this as just one integral of beta mu plus eta 2 to the power of n minus 1 over, oh wait, oh no, that's wrong, sorry. The integral from 0 to infinity, of course, has to be finite. It's the integral from beta mu to infinity that is quite small, right? So this should be switched. So this should be beta mu, and this should be 0, right? So the plus and a minus. Yeah. So this is a function that this stuff is a function that vanishes, that is very quite small for beta mu onwards. So this is actually how you get an integral from 0 to infinity. So it's minus, right, because of a minus here. Beta mu minus eta 1 to the n minus 1 over 1 plus e to the eta 1. Actually, I can just, instead of using eta 1 and eta 2, because these are just variables I integrate over, I can just call them eta, right? Okay. Now, we can expand the numerator in eta over beta mu, right? This is small. So if we expand as a Taylor series, what do we get? This is equal to beta mu plus eta to the n minus 1 minus beta mu minus eta to the n minus 1 is approximately equal to beta mu to the power of n minus 1. This we are bringing sort of out of the parentheses to get this small term here, This becomes 1 plus n minus 1 eta over beta mu minus 1 minus n minus 1 eta over beta mu. Okay? Here we just use the famous Taylor expansion. 1 plus x to the power of n is approximately 1 plus n times x. Okay? Okay, next. This simplifies easily, and you get this is equal to 2 times n minus 1 beta mu to the power of n minus 2 eta. So essentially the 1's cancel and the n minus 1's don't. So we found a fairly nice expression, which is of course an approximation. So this is equal to beta mu to the power of n over n plus 2n minus 1 beta mu to the n minus 2 integral of from 0 to infinity of eta over eta e to the eta plus 1 d eta. Okay, but now we can recognize this integral right here as a Fermi-Dirac integral, right? This is gamma 2 times f2 of 0, and this is equal to pi squared over 12, okay? This is also just a polylogarithm. This is just minus Li 2 of minus 1. Yeah. It's a fairly famous integral, and you can write this as a series, and that this series is the series that Euler calculated. But yeah, so this is equal to pi squared over 12. So this means that gamma n f of n z is equal to, I write this in the following way. I'll write this as log of z, right? Recall that the log of the fugacity is beta mu to the power of n over n plus pi squared over 6 n minus 1 log of z to the power of n minus 2. Now I divide by this gamma function. So this is gamma n, this is gamma n, and so what is this equal to? So finally, f of n z is equal to, I'll factor out this expression right here, right? So this is log of z to the n over gamma n plus 1, right, times 1 plus pi squared over 6 n minus 1 over log of z squared. Okay, this holds when z is much larger than 1, which is the low temperature approximation. Okay, so this is the Born-Sommerfield approximation for the Fermi-Dirac functions, and these are quite useful when dealing with the statistical physics of Fermi gases in a low temperature limit. For example, when studying the heat capacity of metals, which is what our next video is going to look at.